doing that. I'll do my best. What? Who drew it? Who? Oh, you did? Well, take a picture if you need. So, okay, I am going to have to let it go, but I'll leave it up there for a little bit. Okay, let me get the lights adjusted. Make it a little easier to scan the code. Okay. Is it going to go? Okay. All right, so today we're just going to continue and honestly kind of end our discussion on timber and wood. Like I said, this isn't actually going to show up on a homework assignment until a little bit later. And the actual problems that we're going to do with timber are really, really easy. Most of what I'm interested in with your understanding of timber is, at least for the purposes of this class, is more understanding concepts than I'm worried about you doing computations. There is one computation we're going to do, which is really easy, which is I'm just going to show you how to do a board foot computation, which is, again, there's really not a lot to it. But I'll take some time and discuss that. But today's lecture is going to be more focused on the wood products that are available. So the last lecture was focused on sort of like wood science and how we produce, lumber and things like that. Today I want to talk about the available products that we get out of that and their relevant properties for us as civil engineers. I'm going to re-record that video this weekend of the lab report guidelines because I'm also going to try and record this weekend our pre-recorded lecture. I need to have it done by Tuesday because we're not going to have class on Tuesday. We're just going to go straight to the lab. The lecture on Tuesday, so this week is timber and wood. Next week is asphalt. Okay, so we'll do a little bit of discussion about asphalt on Tuesday, and then Thursday maybe a bit more on the computational side. And then the week after is the week before Thanksgiving break, where you all are going to be working on your lab report. Don't forget, if you haven't already done so, submit your 14-day sheets by Tuesday, and then your homework 6 is due Thursday. Okay. So again, next week we're just going to meet at 2 p.m. in the lab. We're going to do our beam tests, and we're going to do our cylinder tests. That's what we're going to do. Does that sound good? All right. Okay, so everybody get the code? Okay. All right, so this is about where we left off. We were talking about sort of the products that we get out of a lumber operation. When we are dealing in timber design, this is going to be a focus of the course next semester. We sort of split the products that we use as structural engineers into two areas. We either have sawn lumber or we have engineered wood products. Okay, and engineered wood products are things like plywood, OSB, glulam, CLT, and really the difference between an engineered wood product and sawn lumber is the introduction of glue. If there's any sort of glue or adhesive that is brought into the manufacturing process, that's what it's for. We'll talk a little bit more about that throughout today's lecture. You're going to hear me mention different terminology for wood products. So let's talk about sawn products. There is a difference between lumber and timber, okay? And there's a specific line that's drawn in the sand in terms of the spec. So dimensional lumber would be things like, the ubiquitous 2x4, 2x6, 2x8, etc. The stuff that you can get at Lowe's and Home Depot, etc. Dimensional lumber is really going to be anything that's 2 inches thick. I say here 5 inches thick, but really it's more 4 inches thick. These are going to be your 4x4 posts, your 2x4s, 2x6s, and so on and so forth. And dimensional lumber is going to be used for light framing, beams that have relatively narrow spacing, things like that. Heavier elements are going to be what we call timbers. Okay, so timbers are going to be things that are like 6x6, 8x8. Things like 8x14. Those are much larger elements, and we call them timbers. Okay, and there is a reason, at least from a timber design perspective, why we delineate a difference between lumber and timber, and that's because we have different design stresses and whatnot that we use for those different components. We also have a separation for round stock, so like piles, utility poles, things like that, maybe some posts and whatnot. And there's different factors that we calculate and whatnot if we have round cross-sections versus rectangular cross-sections like this. And so dimensional lumber, timbers, and round stock are really the three most common products that we use as civil engineers. What do we use lumber for? Well, you know, make a list. You could probably make a pretty extensive one. Dimensional lumber, I think we all probably know what dimensional lumber is going to be used for. It's mostly residential construction, houses and things like that. You will every now and then see dimensional lumber used in maybe some light or small scale commercial design, but not very much. When you start getting into the commercial landscape, you really need to use either heavier elements or what have you. Heavy timbers are going to be obviously for much larger structures and what have you, so you could see heavy timber in all sorts of applications. You know, one of the advantages to timber and wood over steel and concrete, and I mean, it is a real advantage that I don't think we as civil engineers and structural engineers really consider very much, and that is that wood's pretty. I mean, you get really pretty structures out of wooden, using wooden elements. You see, if we're talking about these structures here, so I've got a building and a bridge. Where do you see heavy timber and glue lam and these components used? So you'll see them in a lot of like specialty structures. There's also certain like common classes of structures where you'll see timber used a lot. So like lodges, you see them in churches quite a bit. You see a lot of timber elements, used in religious settings. You'll see, for example, this is an arch bridge that's made out of timber. Really, really pretty structures. And so, like, that's another place where you'll see timber applied is when the aesthetics really matter, okay? There are certain installations and certain facilities that want a certain look and feel to them, and you sometimes can't get that with, an ugly reinforced concrete T-beam. I'm not saying there's anything wrong with concrete, or steel. Don't get me wrong, I'm a civil engineer. Of course I love steel and concrete, but this is great, So that's an area where you're going to see timber applied. I don't want to get too much into specialty items like handrails or decking or things like that, because I'm not saying it's not important, but when I'm thinking of civil structural engineering applications, I'm more interested in larger scale products. And so what do we see in civil and structural engineering applications? We see a lot of panel systems and a lot of veneer type systems. So you'll see structural elements like beams made out of things like LVL or glue lam or what have you. You'll see panel type elements like plywood or OSB or laminates and things like that. And we'll talk about that throughout today's lecture a little bit, and obviously a whole lot next semester. I've got some slides here on the production of wood, and I'm going to be honest, I'm going to skip through this real quick because I really think that video that we watched did a whole lot better of a explanation of this than just these few slides. I thought, again, I really liked that video. But I'll say just a couple things about it. So, as I think I highlighted last time, one of the advantages of using timber and wood in an engineering context is that it is a very renewable resource. We're at a point now where we're really, when it comes to timber harvesting for construction applications, we're planting more trees than we harvest, and we're typically, like, once you plant a tree, you can harvest it about 40, 50 years, so we're doing pretty good in that regard. There was, I think that video was kind of nice because it showed, we spent a little bit of time pausing and looking at the sawing operation, which, there's a couple of, I guess I'll say old school methods where you're sort of selecting right off the bat that we're going to saw the log this way or saw the log this way. But really what's happening is this, where these days a numerical imaging algorithm is basically taking a cross-sectional view of the log, which is collecting using various LiDAR and laser scanners and things like that. It's using an algorithm to optimize the configuration of the cuts in order to generate the most use of the tree that we can get out of it. And so there's not really a lot to say about that. This is really just sort of how we're doing it these days, where we're just sort of letting a computer identify that for us. We saw in the production process how we have to season wood. So if you hear me use the term seasoning of lumber, I'm talking about drying it. And seasoning, I guess the term that's used is because seasoning implies that there is a process to it, and there is. I mean, there are, for example, you have to have certain drying schedules and certain temperatures set for certain species of wood because you don't want the wood to dry too fast. You can get excessive defects, which is something that we're going to talk about today, are the various defects that you can get in a given wooden element. And those defects affect its grading, affect its capacity, etc. There are a few different methods of seasoning. I mean, the simplest is to air dry it, which is, I mean, literally just to leave it outside. I mean, it works, don't get me wrong, but it is slow. And so most modern sawmill operations are going to have some sort of a kiln that will speed up the drying process. And again, there's science to it because, again, certain species you have to dry at different schedules and what have you. So one of the things that you will find is that, so I really like this image because what you're finding, and it's probably exaggerated a little bit, but if you have a tree, okay, so here's a tree, and you can see how we cut out certain elements out of the tree. So you can see, for example, this board right here. Not only does this show the potential defects that you can get out of that, but it also shows changes in defects depending upon where you get the board out of the tree. So, for example, you can get more cupping out of a cut that's made like this versus more checks and shakes out of cuts like here, cuts here near the middle and whatnot. And we'll identify those defects here in a bit. Now, so at the end of the day, what happens is, you have your rough cut lumber, you dry it, and then you will take that dried, rough-cut lumber and then surface it to get the final dimensions, okay? And so this is where, I've got here in my hand a section of a 2x4. This is not 2 inches by 4 inches, okay? This is 1.5 by 3.5, okay? So what's happening is an actual 2x4 was dried probably, for a species like this, probably in a kiln. And there was probably a little bit of dimensional distortion, so we surfaced that out. For any side that's less than 8 inches, we take a quarter inch off each side. So if it's 2 inches thick, we take a quarter inch off this side, a quarter inch off this side, and we get 1.5 inches, okay? If the side is greater than 8 inches, we take off 3/8 off each side and ultimately arrive at our final dimension. So like, for example, if we had a 2x4, we take 2x4 minus this, minus that, get 1.5 by 3.5. So one of the things you'll see, for example, in the timber spec next semester is you'll see a lot of section properties for S4S lumber. And it's like, what is S4S lumber? It means it's surfaced on 4 sides. So you'll see that. You might see surfaced on 4 sides, surfaced on 2 sides, et cetera. So just to give you kind of an idea of why that is what it is, why that is. Okay? How many of you have heard of a board foot? Just curious. Has anybody heard of the term board foot? Oh, not many. Ooh, this is good. I like this. Okay. I'm sorry. The artwork's got to go. I'm sorry. Everybody's going to boo me now.
Yeah.
I'm sorry I erased the board image. Okay. So, what is a board foot? Okay, so a board foot is a unit of measurement of lumber, and the primary purpose of a board foot is used for cost estimation. Okay, so a board foot is one board foot is essentially defined as a plank of wood that's 12 inches by 12 inches and 1 inch thick. Okay, And the main value of it is if you're doing a given project, like for example, let's say you're building a, I don't know, like a shed in your backyard, okay? And so you figure out how many 2x4s you need, you figure out how many 2x6s you need, et cetera, and you ultimately arrive at a computation of board feet, okay? And I'll show you how that works here in a second. But the number of board feet can be used as a cost estimation tool. Lumber is typically priced as a cost per board foot, okay? So being able to distill a given project into this is how many board feet I need can give you a pretty simple example as to, a pretty simple way of figuring out how much that lumber is going to cost, okay? Computing board feet are really, really easy, okay? So just a super simple example, okay? Let's say I've got 2x4s, okay? And let's say that I've got, I don't know, 36 of them, and each of them are 8 foot long, okay? So the way that you compute the board feet is pretty easy, okay? So the board feet computation is we just take the dimension 2x4, and by the way, we're using nominal dimensions, so we're not using the 1.5 by 3.5. So we're using the nominal dimensions, multiply that by the length, multiply that by however many of them there are, and we need to take one of these and convert them to feet, because this is in inches, this is in inches, this is in feet. So we need to convert one of these to feet, so just divide the whole thing by 12. That's a board foot calculation. That's it. That's it. So if I wanted to calculate the amount of board feet of 36 2x4s that were each 8 foot long, I would just take the product of all those numbers and divide them by 12. That's it, okay? So I think this one comes out to 192. So that's 192 board feet. That's it, okay? And then we would use that as a means of estimating. So you could look up lumber prices and say, well, a board foot of Douglas fir costs this much, this many dollars per board foot, multiplied by 192, that's about how much it's going to cost. That's it. That's basically your board foot computation. There are a couple of notes that are worth mentioning with board foot computations. So probably the biggest one is that for products where T is less than 1 inch, use T as 1 inch for board foot calcs. And so this basically applies to like plywood, okay? So if you were trying to figure out the amount of board feet in a 4 foot by 8 foot sheet of plywood that's 3/4 inch thick, don't use 3/4 of an inch, just use 1 inch, okay? Again, this is a cost estimation tool for the purposes of getting, a dollar figure on it. Okay, so that would probably be the biggest thing there, and 2 round lengths. Right? So if you had like a length of 12 foot, 3 inches, just use 12 foot. That's it. I mean, there's not really a lot to say about computing a board foot for a given product. It's pretty simple. Okay? Does that make sense? Is everybody okay with that? Everybody good with their board foot seat computations? That was a joke.
Is the 12 on the denominator constant?
Yes. That's a great question. So what's happening is, here's why it is. So, okay, let me redraw this maybe a little bit. So this is a graphical representation of a board foot, right? So it's a 1 foot by 1 foot by 1 inch thick piece of wood. Okay? Bless you. So if I have a 2x4, right? A 2 inches by 4 inches by 8 foot long. Okay? So what's happening is this is in feet, this is in feet, this is in inches. This is in inches, this is in feet, but this one's in inches, right? So what I'm going to do is take this and divide by 12 to get this into feet so that it's converted. So yeah, that's a constant. Does that make sense? Yeah. So a board foot is basically like 1 foot times 1 foot times 1 inch. So, make sense? That's a good question, by the way. Sound good? Okay. Don't worry, we'll spend a lot more time looking at that next semester. Okay. Let's talk about grading, and I want to so here's what I'm going to do. Okay, the first thing, I'm going to go back to that slide, but I want to show you this. This comes out of your textbook, but I want to be clear, we're going to see a lot of these for those of you that choose to take timber design next semester. This comes out of the NDS specification. So let me give you a sneak peek into timber design next semester. Okay, so let me go to my OneDrive. Here's my little timber design folder. I put 2 versions of the specification in my OneDrive. Let's do the newest one. So the way that timber design works, there's 2 documents. There's what's called a code and a supplement. So the code will tell you, here's how to calculate the bending strength of a wooden member. Here's how to calculate the shear strength of a wooden member. Here's how to calculate the shear strength of a bolted connection or whatever, right? And then the supplement will tell you, here's all the reference values that you need to use when you're doing your computation. So if I go into the supplement, okay, let's just sort of show a couple things. So if I go to, for example, the section properties document. Okay, so here's the section properties document. And then if I go down here, you'll see things like, okay, here's one. Let me zoom in a little bit. So I think you could probably see where this would be necessary. So for example, if I was using a 2x4, here's the nominal size, here's the actual size, here's the area, the moment of inertia, the section modulus, and so on and so forth. We can use that for the purposes of calculating stresses and deflections and so on and so forth. Okay. Now, the other thing you'll see is in the supplement are these reference design values. We're going to spend a lot of time looking at this next semester. Okay. So, so what these reference design values show is for a given species of wood, it'll show you what are the various stress limits under different loading conditions. And so they vary as a function of wood. So there's tons of these things. So like a really common one, for example, hem fir. That's a really common one we'll use next semester. And so there are various, so if we look at hem fir, the first thing we'll see is we'll see a series of grades. So we'll see select structural, number 1, number 2, number 3, etc. And then based on the grade, we'll have limiting stress values. And those stress values change, and they sort of get lower as the grade goes down. Okay? And so your textbook has like a simple example of that, but there's a lot more that we'll see next semester. Okay? So one of the things I kind of wanted to show, let me see if I can find the, I think it's this one. Was it this one? I found a resource, and it had a really cool image of the grades of wood. I really kind of liked it. Yeah, oh yeah, here we go. Okay, so this is, it probably seems somewhat, dry, but I really think this is kind of a nifty guide, and I think it works really well to sort of show visually what's going on. So, kind of serendipitous, I found the page for hem fir. So this is a wood products guide, and it shows the classifications that you get as a function of grade. And so there's a couple of different ways that we grade lumber. The 2 most common is that we'll either rate lumber using machines, or we'll visually grade it. Most lumber is visually graded because it's a lot faster. And so what we're seeing is structural framing, and we're seeing grades as we go from left to right. And so this is what number 2 lumber would look like, and this is what select structural lumber would look like. And one of the things you'll notice, I mean, just visually, if I scroll all the way down here, you will see less defects per length. You'll see a more uniform color. You'll see there's a lot here that sort of affects the quality of the grade. And ultimately that matters because those grades result in higher capacities and whatnot. So for example, if you utilize select structural, let's say this is eastern white pine. If you use select structural eastern white pine, you can count on 1250 psi of bending stress. Whereas if you use number 2, you can only count on 575. Now, what happens with those higher grades of stresses? the lumber costs more, right? And so this is why if you're going to purchase lumber or purchase timber products, the higher the grade, the more expensive it is. But also the higher the grade, the lighter the sections that you're using. So it's a trade-off, lighter equipment on site, faster builds, but you might be paying more. So it just depends. So there are visual appearance grades as well, and I'll show you some specific stamps of that related to, in my head I'm thinking about glulam products. There's glulam products that are meant for visual appearance, and then there's glulam products that are only meant just to hold up loads. So you'll see, for example, in some spec houses where they'll use like glulams like under the first floor to hold up a big section of the house. It's this really, really big element that's hidden so that nobody can see it. So it's got this different appearance classification. Certain elements have a really high appearance classification in case they're going to be stained or whatnot, so that affects things as well. To be honest, we as structural engineers care more about the mechanical properties than we do the appearance ones, but the appearance ones do matter if that's what your client wants. Now, again, as we mentioned, wood is a very non-isotropic material in that it behaves differently depending upon which direction you're loading it, okay? So there's a lot of different stuff here, and I'll say a few things about it. Again, this is a big topic for next semester. But we have bending, so here's this element. Here's how it would behave if we took it and we bent it. Here's how it would behave if we took it and we applied tension parallel to the grain. This is what would happen if we sheared it, etc. One of the things that you'll find is, for example, compression. So there's two different ways that we can load an element in compression. Compression parallel to the grain would be taking it and pressing it like this, okay? Whereas compression perpendicular to the grain would be taking it and pressing it like this. And we do have to assess both. For example, here's a beam. The beam sits on a sill plate. This is the reaction. So there's a reaction right here. We have to ensure that the wood element is not going to crush under that big support reaction. So that's a compression perpendicular to the grain that we're going to have to assess. If we're looking at columns, we're going to look at compression parallel to the grain. Okay? Here's something else that's a little weird. Why are there two Young's moduli? Why is there a modulus of elasticity and then a minimum modulus of elasticity? That's weird. Why? Which one do you use? Well, it depends on what calculation you're doing. So if you're just looking at beam deflections, here's a beam, we want to see how much it deflects, we use the modulus of elasticity. But if we're doing stability calculations, if we're trying to figure out how much an element can hold up before it buckles, we use a minimum modulus of elasticity. So that's one of the things about timber design. It is a very detail-oriented computation. The other thing that will definitely become the star of the show next semester are the adjustment factors, okay? And I'll sort of give a highlight on this here in a little bit, but what we're looking up here are what are called reference design values. We do not use reference design values at the end of the day when we're doing timber design. We use adjusted design values. So these values that we look up, these are ideal world conditions. And what we have to do is take these values and adjust them to real world conditions. And unfortunately, we have to adjust them quite a bit. We have to adjust them for temperature, for moisture, for flat use, for size factor, for stability, for, incisions. Like, it goes on and on. And so, unfortunately, there are a lot of factors in timber design. Timber design is a factor science. And so, most of the time, those factors are one in normal operating conditions, but every now and then they're not. And so, you have to take that into account. Okay. Let's talk about grading defects. So why would an element of wood not be graded perfectly? Like, why don't we just grade every piece of wood select structural? Well, there's a number of reasons. Ultimately, what we care about is its mechanical properties. And so those mechanical properties can be affected by the characteristics of the wood. For example, okay, I don't know if you all can see this on this piece of wood. Okay, does everybody see this part right here? Does everybody see that? Everybody see this right here? There's like a sort of a separation along the, or sort of perpendicular to the grains. Everybody see that? Okay, those are fibers in this element that are, separated. Okay, if I take this and I bend it, it's not going to behave as well if it was all uniform like it is down here. Okay, I've got checks in this element. I've got shakes in this element. I got a little bit of a wane right here. So there's all sorts of defects that are going to affect whether or not it's going to be select structural or number 2. And again, this is coming from the earth. That's just going to happen, okay? So what I'll just say, so where do defects come from? I mean, they come from just, the fact that this comes from the earth. It comes from just, the seasoning process. Again, as I mentioned last time, these things are yummy. They can be yummy to parasites and to organisms and what have you. There can be issues in the processing. I mean, when you're processing that much lumber in a given day, that's going to happen. So what type of defects will you see in a given wooden element? Well, one of the most common ones you'll see is a knot, okay? I'm sure everybody knows what I mean when I say a wood knot. So if, let me ask you a question. Let's just make sure we're all kind of on the same page here, okay? If you have a tree, okay, so here's the tree, okay? And I have a 2x4 here that came out of this section of a tree, and a 2x4 that came here. Which section's the most likely one to have a knot, 1 or 2? The one on top. Knots come from branches, right? And branches are going to come from this side of the tree, not the middle, right? So depending upon where the board came from inside the tree, you're going to have the presence of a knot, okay? Now what about shakes and checks, okay? So I'm going to do my best to draw this here on the board. It's going to test my art skills a little bit. I kind of like this board for this reason. So I'm going to sort of look at the cross section of this board, okay? And I'm looking here. This must have come from a tiny tree because here's the center and the rings are sort of coming out like this. So it's kind of doing this whole thing. Okay, so there's that, okay? And so one of the things you'll see here is we're getting some separations like here. Like there's actually like a big old separation right there. And I'll sort of draw it like that, okay? And you can kind of see it right here. This is a shake, okay? All right? But we're also seeing some separations the other way. Like there's actually some separations. So these are sort of aligned with the rings. And then there's also some separations that are going like this. This is called a check, okay? So you're going to see the term shake and check. I wanted to make sure you knew what the difference was. Shakes are sort of going along the rings. I think these images could probably be a little bit better. But shakes are going along the rings. Checks, because what a shake is it's basically the rings separating from one another, and a check is going across them, okay? One thing you'll also see is what's called a wane. And so a wane happens, let me see if I can draw this here, okay? So a wane happens when the board comes from the edge of the tree, and so you don't get this nice pretty cross section, okay? Instead what's actually happening is you're getting, you might have like, it might look like this a little bit. I'll just say it, if you get lumber from a big box store, that happens. Go check all the stock of lumber at some of the big box stores, and this happens. It's nothing against the big box stores. Like that's just the earth, it just is what it is. So there are a couple of other things that you can see with grading defects. You can see like different colorations or sap streaks or what have you. But in terms of the what I'll call inherent geometry, these are probably the most common defects that you'll see. So this one right here, that's a wane. Okay. You will also see, and you can also see some splits, by the way. So splits would happen if you're just seeing like a separation, like along the length. That's a split, and what have you. Now, the other thing that you will see is changes in the geometry with it curving or warping or so on and so forth. And I mean, if you ever go to any, lumber store, whether it's a lumber supplier or a big box store, and somebody's buying lumber, you will probably see them if they're doing a big project. You'll see them grab a few boards and sort of like hold them like that and seeing if they're straight and plumb. You've probably seen that, right? So what they're doing is they're trying to ensure that the element is dimensionally stable. And again, these come from the earth, so that's going to happen. Okay. What can you get? So let's go through the various things that can happen. So warping, in general, is the adjustment from a prismatic geometry from the drying process and the internal stresses in the tree. So I'll say one thing about internal stresses in the tree. The tree is around, circumferential growth, and you're cutting a rectangular section out of it. The tree wants to stay like this, and so when you cut it into a rectangular cross-section, it's going to kind of bounce back, okay? It's going to kind of change a little bit. It's almost like these fibers are a big old rubber band stretched around the tree, and then you cut it out, you're kind of relaxing it a little bit. So it's going to deviate from a prismatic cross-section just for that reason. That's called a release of residual stresses, okay? Now, what kind of warps can you get? You can get bowing. So that's sort of almost like a flexural defect across the length of the span. Bowing and crooking are sort of the same thing, but bowing is happening about the minor axis and crooking is happening about the major axis. Cupping and twisting is sort of a cross-sectional defect, so cupping is the element sort of doing this, and twisting is where it's just sort of torsionally warping along the section. Okay, the defects kind of make sense. I'm hoping that's pretty straightforward. Okay, specific gravity. Okay, so specific gravity is inherently variable from wood species to wood species. So, for example, if you go back to this supplement that I was showing you, okay, so you'll notice over here on the right we get different species of wood. So, for example, if we're doing, eastern hemlock, tamarack, the specific gravity is 0.41, whereas if we're using hem fir, it's 0.43, okay? So you'll find that the specific gravity does change from species to species. But what's happening from species to species is the following. So first off, the wood is basically a combination of cellulose, water, and air, essentially. And the actual fibrous materials, the cellulose that make up the wood, has a consistent specific gravity of 1.5. Okay, so the actual material is heavier than water. But what's going on is, so from species to species, you have different sizes of the cells. Those also, there's going to be different moisture contents and so on and so forth. So the structure of that material and the amount of water inside it is going to change the specific gravity. And you can go from like balsa to sycamore and get some pretty pretty wide ranges, okay? So yeah, but like if you were to ask me without knowing anything, what value should you use as a specific gravity, I'd probably use something like 0.35 for most species of wood around here. So 0.35, 0.4, something like that. Okay. Wood is I don't want to have a whole lot to say here. Wood's a fairly good electrical insulator when dry, but it's typically not. Just make sure that you're careful with wood and electricity, but I think that's probably a pretty common note here. As we said, so let's talk about some mechanical properties. So what I have here is the Young's modulus of wood, but this is the Young's modulus for, this is the one that we would use for like serviceability computations. For stability computations, we reduce this a little bit. So for regular old serviceability computations, Young's modulus for wood is somewhere between 1 million or 2 million psi, dependent upon the species and what have you. And we can test that for, using a lot of the different tests that we've used this entire semester. when it comes to tensile strength versus compressive strength, tensile strength is higher. I mean, wood is a material that does like to be yanked on more than it likes to be pressed on. But the tensile strength parallel to the grain is incredibly high compared to tensile strength perpendicular to the grain. So if I take this and I yank it like this versus yanking it like this, yanking it this way, it's about 5% as strong as if I yank it like this. Like, we pretty much assume the tensile strength this way is 0, okay? So just keep that in mind. Okay, this is where we start to have fun next semester, okay? So, like I said, those reference values that we look up are just that, reference values in ideal land, okay? We have to adjust that for the real world, okay? So one of the biggest things about wood is an incredibly variable material mechanically dependent upon its in situ conditions. One big effect that wood will have, or one big parameter that affects wood's behavior is the load duration, okay? If you take an element of wood and put, let's say, 100 pounds on it, okay, and you put that 100 pounds on there for 5 minutes, the wood will respond better to that load than if you put that 100 pounds on it and leave it there for 20 years, okay? Wood has much higher capacity if the load is applied over a short duration. Under loads that are sustained over a long period of time, wood will continue to deform. This is a material phenomenon known as creep, okay? So if you look at the wood, if you look at wood's behavior as a function of time, it's almost like instantaneous loads. Like if you apply a load for a second, the wood's going to be twice as strong than if you leave it on there for 10 years or permanent. So for those of you, how many of you have had concrete design? Some of you might have had concrete design. You might have remembered immediate versus long-term deflections. And did you talk about that in concrete?
You mean like reinforced?
Yes.
I'm at it right now.
Have you gotten to immediate versus long-term deflections yet? You,
I think so.
we'll talk about it in timber, I know that. Okay. Wood does have a pretty good response, or the ability to absorb vibrations. To be honest, I'll just say it, that doesn't really matter much here, but where would we care about absorbing vibrations? Like roller coasters is one. I'm also thinking about a region of the country. Give me a state where we would care about absorbing vibrations.
California.
Why California? Earthquakes, yes. So the ability of a material, that's good. The ability of a material to absorb vibrations, it's response called damping. That is a really important facet if you're designing an earthquake-prone zone. So wood's not bad at that, but I'm going to be honest, at least here in West Virginia, not really that big of a deal. I will say, I have this statement here in the slides that the strength of a wood structure is governed by the strength of its connections, and that's true. We're going to spend a good bit of time in timber design looking at connections, but this is also true really of any structural system. You know, if a member fails, the member fails. But if a connection fails, multiple members fail, because multiple members connect at a connection. That's what a connection is. So connections are treated with a little bit higher factors of safety, let's just say. Your resistance factors and whatnot are a little bit more stringent in connection land than they are in member design land and what have you. I'll just say a couple things about mechanical testing. A lot of what we do with mechanical testing of wooden specimens mimics what we do with concrete specimens or steel specimens. We can still, do a tension test, do a bending test, do a compression test, and what have you. The big thing that you have to do with testing wood specimens is the wood specimens have to be clear. So they have to be completely free of defects, no knots, no geometric issues. So that's probably the hardest part. But once you get the specimen, it's really no different than any other test that you're going to do. We're going to do these tests next week on our concrete beams. So we'll do those together. We're not going to do them on wood, but we'll do them on our concrete specimens and whatnot. This is going to be fun next semester because we are going to have an adjustment factor for every one of these. This is what I meant. Now, every one of these well, not every one of these are going to have a value in every consideration. Like a lot of times, these are going to be 1. So like I'll just give you like a quick example. So if you're designing, let's say, you know, you've got your patio, right? Here's the grill. Here's, you know, Mr. McCoy grilling, you know, and you've got, you know, wooden elements, you know, supporting the floor, right? Okay, and this is, we'll say outside, you know, or in an area like this, right? So using species of wood that are available, let's say, in this area, okay? So here's a suggestion. This is going to be a lookup. This will probably be 1 if it's shielded. This will probably be 1. This will probably be 1 in those instances. This will probably be something we have to compute. That's 1. That doesn't apply. We'll have to take care of that when we do that calculation, but we have to do that anyways. We don't have to worry about that. Don't have to worry about that. That one will probably be 1.15 depending upon the geometry. So there's a lot of factors, but they're pretty easy to determine once you get an understanding of what they all mean. That's our goal next semester. Okay. Like I said, there are some disadvantages of timber, and one is that it's yummy. So we can have various fungus or other bacteria that can invade a wood species and cause issues and whatnot, which is why, I mean, you know, for example, I mean, if anybody's done any sort of remodeling or have your parents done any remodeling or anything like that, you know, for example, when you do your kitchen or your bathroom, you know, you use treated wood and whatnot. Why? Because it's exposed to moisture and things like that. So, I mean, that's just, you know, you just got to take that into account. There are some other things to worry about, termites, you know, beetles and whatnot. It can happen. So yeah. What else do I want to say? Oh, I want to talk about engineered wood products. This is kind of what I really want to talk about here. Okay. And we'll go through this pretty quickly, and then we'll call it for the day. So everything I've been talking about is sawn lumber, okay? And as we've mentioned, or as we saw in the video last time, so sawn lumber, you know, we're really good at optimizing the use of the tree, and we are able to get a very efficient use of it. But cutting out 2x4s out of a tree is not a perfectly optimized process, and it never will be. There will be chips of material out there. There will be little bits of bark and little bits of this and little bits of that. It's an organic product, so there's a lot of variability there. There are ways of improving not only the dependability and the uniformity of wood products, but there's also ways of expanding things like span length, expanding performance overall by introducing glue. Okay, and engineered wood products are basically introducing glue and other manufacturing processes to get consistent mechanical properties out of the pieces that we generate. So some of these you're probably familiar with. So take plywood, okay? So like it's super simple, but in terms of uniformity, like I mean, let's talk about plywood, okay? So how does plywood get manufactured, okay? So the first thing that we do is we take a tree. So here's a tree, right? And we basically take the tree and we spin the tree, right? And we run a blade like this, and we spin the tree, and we basically cut the tree into a big old sheet. So the sheet goes like this, almost like a roll of paper towels. The tree just whoop, shuts out. And then what we do, I mean, it's super simple, but we take the plies of tree, and we lay one like this, one like that, one like this, one like that, one like this, one like that. And suddenly, we now have a board that behaves largely the same in one direction than it does in the other, right? Simple, you know. We also, by doing it this way, we don't have to worry about some tree where we're cutting a board out like this and then cutting a board out like this, and then this material's all wasted. We're literally using all of the tree, okay? Now, what are the disadvantages? Well, we've got to include glue. It's a little bit pricier, but we are using the tree more effectively, okay? All right. So, what else do I want to say about this? I don't want to get too far into grading plywood and things like that, because again, I'm stealing my own thunder next semester. I do want to talk about some of the longer products here. I'm going to skip ahead to talk about, because we don't really use like particle board and whatnot for structural applications. You've probably used particle board in, I mean, I know I got the entertainment center from Walmart. I mean, that's all particle board and whatnot. We are going to talk a little bit, though, about these. Anybody seen these in wood eye joists before? You might have them in your house. This is an engineered wood product, and these are used as floor joist elements in residential and even some commercial applications. The funny thing is, so if we were to try and without any resources available, and this is one thing I'll say about the engineering community, which is kind of nifty. If we were without any resources at our disposal, if we tried to develop a formula or a means of computing moment capacity or shear capacity or things like that of these elements, it would be awful, because these are actually mechanically really complicated elements. I mean, we've got particle board squashed up with some dimensional lumber. So how do we calculate things like moments of inertia? How do we calculate shear capacity? This is actually a really complicated problem. We don't have to worry about that, because what we're talking about is a space where the manufacturers of these products publish guides. And if we have, for example, a TJI joist, we can look up the manufacturer spec. Here's the moment capacity. Here's the shear capacity. Here's the EI for deflection. And so we have a problem, just pick one that works. So it's actually pretty nice in that regard. To be candid, most of these manufacturers of these proprietary products, they want you as engineers to spec them, so they're going to make it easy for you, you know. You just need to understand how they work. So that's what we're going to be talking about next semester. Last thing I want to talk about is Glulam. So Glulam is a really, really nifty product. If you've ever seen a Glulam beam, they look sort of something like this. One place, at least, that I've seen one very available, like that you could see out in the environment, is at the Barbersville Library. They have these elements right out front. Those are Glulam elements. So if you're ever around there, the new library they built out there, those are Glulams. So what is a Glulam? A Glulam is basically taking dimensional lumber and stacking it up into these like layers and gluing it and getting a big old beam. Okay. Now, one of the nice things about a Glulam beam is that you can increase the length of a span very, very easily. So, for example, if you're using dimensional lumber does not come in 60-foot lengths. It doesn't, right? You can't get a 2x4 that's 60 foot long. So, how do you get a Glulam beam that's 60 foot long? Well, you have a lamb here, a lamb here, a lamb here, and then maybe this lamb, then like that, then like that, then like that, then maybe this. So you're layering the boards on top of one another, and you're sort of scattering where the boards butt up across the span. Not only are you doing that, but you can also evenly space out the defects, evenly space out any checks or shakes or anything like that. So you can get really, really uniform products that are really, really big and can support a lot of load, and it can also support a lot of load at long spans. Okay. One thing we'll talk about next semester is the difference between a balanced Glulam element and an unbalanced Glulam element. So, in general, if we're talking about Glulam for a beam, okay, one of the other things that we can do is we can specify the species and the grade of wood. And a lot of times what we'll do is we'll put sort of our less quality wood in the middle and our better quality wood on the top and bottom. Why don't we put the better wood on the top and bottom and the not so great wood in the middle? Why do we do that?
Under load, that's where it'll experience more tension and compression.
Exactly. Sigma equals my over I. And wood is a material that like tends to be governed more by its bending capacity than it does its shear capacity. So the highest bending stresses are at the top and bottom. So you put the better wood on the top and bottom. Difference between a balanced beam and an unbalanced beam is an unbalanced beam is meant to be simply supported. So it's meant to be just beam, beam, smiley face. Whereas a balanced beam is meant for an application like this. It's like if you have post, 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 and you have a big old beam spanning all of it. This is going to be smiley face, frowny face, smiley face, frowny face. So if you need it to be, either way, you would want to use a balanced arrangement. What's funny is if you look at an unbalanced beam, I kid you not, if you look at an unbalanced beam, like here's the beam, and here's the beam, and they have a big label like this right here. It says top. And what that means is that that's supposed to be on top. And then you're the engineer, you go to the site, and you look up and you see the word top. And you go, that's on the bottom. They put that in wrong. So, like, one of the, I'm not kidding, one of the problems that we might be doing next semester is I'll give you a glulam beam and I'll have you analyze it upside down. Because that happens. I'm just being honest with you, that happens. So, it stands for turnover, please. So, I'm such a dork, I know, it's okay. All right. I'm glad I can provide the entertainment value. All right. Any questions? All right. Hopefully I didn't run you away from timber design next semester. That's all I got, everybody. I'll see you.